In this course, the fire hazard engineering team set out to solve a real-world issue, improving indoor air quality by making clean, sustainable cooking fuels. Firewood and charcoal produce harmful emissions when used indoors, while briquettes made by compressing waste material like sawdust offer a safe, long-burning alternative. Briquettes also promote sustainability as they are repurposing waste materials into a cleaner energy source.
Our main objective was as follows: build a portable yet reliable device that compresses biomass into solid, transportable briquettes. The constraints for this project include a budget of $230, a 30-pound weight limit, compatibility with standard outlet of 120-volt 15-amp power, and strict safety requirements around moving parts and heating elements. After evaluating multiple ideas through research, calculations, and testing, we ultimately chose a linear actuating extruder system. It provided the best balance of cost, reliability, and manufacturability. Additionally, we set ourselves the goal of producing at least 1 inch of briquettes per minute.
Here's how the prototype works. First, sawdust is loaded into the hopper where it is automatically guided into the compression chamber. A linear actuator then drives the material forward, applying high pressure inside the heated chamber. The natural lignin in the sawdust melts, binding the particles together. Finally, the formed briquettes are extruded out the end. They are then collected, ready for transport and burning. Taking a closer look at the control system. A simple Arduino microcontroller manages the entire process. The program initially waits until the internal temperature of the extrusion chamber reaches 160 degrees Celsius. Once this target is met, the linear actuator begins cycling back and forth to compact the material. Heating is maintained through a PID control system, which uses real-time input from a thermocouple to adjust the heaters, ensuring stable operation around the target temperature.
As you can see, a variety of manufacturing processes were used to create this prototype, including 3D printing, welding, lathe machining, and manual assembly. This allows the device to be cheap and quickly produced in non-load-bearing components, and strong enough to withstand the 6,000 newtons of force created by the linear actuator where it needs to be. Compared to our original goals, the prototype performed well. We successfully produced strong, transportable briquettes, and we achieved a production rate of 10.2 cubic inches per hour. The briquettes are high quality, and they hold their shape under load and burn for a long period of time.
If we had additional time, resources, and funding, there were several improvements we would make as a group to enhance the design. First of all, we would upgrade from a linear actuator design to a dual roller system. This was our initial design as it produces briquettes extremely quickly and efficiently. However, it requires a significantly higher budget and more time to adjust compression, speed, and heating methods. The next upgrade we would make to our system would be to implement a fully automatic feeding system to simply streamline the operation. In addition to that, we would simplify the design to favor welded joints over mechanical fasteners to reduce the time of manufacturing. All of these improvements together would multiply the briquette production rate and enhance structural integrity throughout the whole design.
In summary, our prototype demonstrates a practical, manufacturable solution for producing sustainable, clean burning briquettes. It successfully meets the objectives and metrics we established at the beginning of the project to produce at least 1 inch of briquettes per minute during testing. This prototype provides a foundation for further development towards real-world applications.